Hello everyone, myself Dr. N.C.H. Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's session on Cauchy's integral formula. Today I am going to introduce the Cauchy's integral formula and the generalized Cauchy's integral formula, and also we solve some problems on Cauchy's integral formula. In the last session we have discussed about the Cauchy's integral theorem and some problems on that. Also, we have verified the theorem for the given function through the given curve. Now here, what is the Cauchy's integral theorem? The statement: if f of z is analytic everywhere on and within the closed circle C, then the line integral of f of z dz vanishes, 0, along that curve. So, if the function is analytic at each and every point on the circle and inside the circle, then the line integral is equal to 0. For example, so this is some circle C. The function f of z is analytic at everywhere except at a point, for example, at this point A. At this point A, the function is not analytic, which is inside the circle. Then how to evaluate the line integral along that curve? So to find this line integral, we apply the Cauchy's integral formula. For example, if this point A is outside the circle, now the function is analytic everywhere inside the circle, then we can apply Cauchy's integral theorem. According to this theorem, the line integral is equal to 0. But if this point lies inside the circle, then we apply Cauchy's integral formula. So here we need to recall the definition: singular point. A point z equal to A is said to be singular if the function f of z is not analytic at z equal to A. That means the point at which the function is not analytic, or the point at which the function ceases to be analytic, or we can say that the point at which the derivative of f doesn't exist, is called singular point. So if the derivative of f doesn't exist at z equal to A, then it is said to be a singular point. And if that singular point is outside the circle, simply the line integral is 0. If it is inside the circle, then we have to apply Cauchy's integral formula. The Cauchy's integral theorem fails since the point lies inside the circle. So we cannot apply here. In that case, we apply Cauchy's integral formula. So today I am going to discuss about that. If f is analytic on and within a simple closed contour C, except at a point z equal to A, which is inside the circle C, then f of A is equal to 1 by 2 pi I into line integral of f of z by z minus A dz. So this is the result by this Cauchy's integral formula. And here the main point is the point z equal to A is a singular point. The function is not analytic at z equal to A, except at z equal to A. At each and every point inside the circle or inside the curve, the function is analytic. But at z equal to A, it fails to be analytic. That means the derivative doesn't exist. So that's why in the denominator here, in the integrand, the denominator we have z minus A. So how to find those singular points? Singular points can be obtained by equating the denominator to 0. So z minus A equal to 0, z equal to A is a singularity. So at z equal to A, the function fails to have a derivative. Hence it fails to be analytic at z equal to A. If that point is in C, we cannot apply Cauchy's integral theorem. In that case, we have to use this Cauchy's integral formula. Of course, the formula gives the value of f of A as an integral 1 by 2 pi I into integral of this. But we use this Cauchy's integral formula to evaluate the line integral. So, if any line integral is in this form, some function of z, f of z by z minus a with the singularity dz, the value of this line integral is equal to this 2 pi I comes to LHS 2 pi I into f of a. So, using Cauchy's integral formula, we can evaluate an integral of this form f of z by z minus a. The result is 2 pi I into f of a. If you apply Cauchy's theorem, the result is 0. Integral of f of z dz is 0. There is no particular format for that function. But to apply integral formula, the denominator is having the terms like z minus a, where a is a singularity or singular point of the function. And the result is 2 pi I into f of a. Similar to this, the generalization of Cauchy's integral formula. Again, the similar statement, f is analytic at everywhere on and within circle except at a point z equal to a, but is having, so here you can see this order. Sometimes we may have z equal to 1 is a singular point of order 1, but sometimes it may be of order 2, 3, 4 and so on. That depends on z minus 1 power n. For example, we have z minus 1 power 3, z equal to 1 is a repeated value 3 times, that repeated 3 times. So, in such cases, f power n of a is n factorial by 2 pi I into line integral of f of z by z minus a power n plus 1 dz. So, using this, we can evaluate the line integral which is in the form of f of z divided by, previously we have z minus a power 1, that is Cauchy's integral formula. Now, generalization of that formula. So, power something n plus 1 dz, that is equal to 2 pi I into f power n of a by n factorial. So, this is the formula that we need to use in the case of evaluation of functions of this form, f of z by z minus a power n plus 1. Now, I am going to discuss some problems on the same. Now, coming to the first problem, evaluate the line integral along the curve C, where C is, first question mod z equal to 5, second question mod z equal to 2. Let us solve this. Coming to the solution part, we need to evaluate the line integral z square plus 4 by z minus 3 dz. So, integral f of z by z minus a, this integral is in this form, is equal to integral z square plus 4 by z minus 3 dz. From this, it is very clear that f of z is z square plus 4 and the singular point z equal to a equal to 3 here. In place of a, we have 3. Now, the first question, we need to evaluate the line integral along two different curves. First question mod z equal to 5, second question mod z equal to 2. So, here the singular point is z equal to 3 and this point lies inside the curve C equal to mod z equal to 5. Now, what is this mod z equal to 5? It is a unit circle. It's a circular. Just delete this. Mod z equal to 5 is a circle with center at origin and radius equal to 5. And here the point z equal to 3. Obviously, this point lies inside that circle. Therefore, we have to apply Cauchy's integral formula. By Cauchy's integral formula, integral f of z by z minus a dz along the curve C is 2 pi I into f of a. So, integral z square plus 4 by z minus 3 dz is equal to 2 pi I into f of 3, a equal to 3. So we have f of z. So 2 pi I into 3 square plus 4. 2 pi I into 9 plus 4, 13. So the answer is 26 pi I. If this point lies outside the circle, simply we can put 0. But here z equal to 3 lies inside the circle. Hence, by Cauchy's integral formula, the value is 2 pi I into f of 3, which is 26 pi I. Now coming to the second curve, what is the second curve? Mod z equal to 2. So it is a circle with center at origin and radius equal to 2. And the singular point is z equal to 3. So this z equal to 3 lies outside the circle mod z equal to 2. Since here the radius is 2 itself and here the point is 3, which 3 is greater than 2, hence it lies outside the circle. That means, therefore, f of z is analytic on and within the circle mod z equal to 2. Therefore, by Cauchy's integral theorem, the line integral f of z dz along C will be 0. That implies sum f of z by z minus 3 dz along the given curve mod z equal to 2 is 0. So here the point lies outside the circle, hence we apply Cauchy's integral theorem and the result is 0. Whereas in the first problem z equal to 3 lies inside the circle, so we apply Cauchy's integral formula and the value is 2 pi I into f of a, where a is 3, 26 pi I. So like that, we have to check first, we have to identify the singular points. Then check whether the singular point lies inside the circle or outside the circle. If the singular point lies inside the circle, simply we apply Cauchy's integral theorem and the answer is 0. If the singular point lies outside the circle, then we have to apply Cauchy's integral formula and the value is 2 pi I into f of a. Similarly, let us consider another problem. Here, let C be the circle mod z equal to 3. So, the circle C is mod z equal to 3. A circle with center at origin and radius equal to 3. Described in positive sense. Let g of a equal to line integral along C 2z square minus z minus 2 by z minus a, where a not equal to 3. Now show that g of 2 equal to 8 pi I. So if we have g of a, we can replace a by 2. Let us find g of a first. G of a means this integral dz. So this integral can be obtained or evaluated using either Cauchy's integral theorem or Cauchy's integral formula. That depends on the singular point, whether it lies inside the circle, outside the circle or inside the circle. So here the singular point is, z minus a equal to 0, z equal to a. And we don't know the exact value of a here, but the circle is with radius 3. So there are two possibilities. Here z equal to a may be inside the circle or outside the circle. Mod z equal to 3. That depends on a. But of course here a is not given, the value is not given, but we can continue with that a itself. Now in the first case, let z equal to a lies outside the circle, mod z equal to 3. That is mod a is greater than 3. Then by Cauchy's integral theorem, line integral f of z dz along C is 0. Simple. Since the point lies outside the circle. For example, second case, let z equal to a lies inside the circle. If it lies inside the circle, then by Cauchy's integral formula, the line integral of f of z by z minus a over along C is 2 pi I into f of a, and here 2z square minus z, 2z square minus z minus 2 by z minus a dz. So here f of z is 2z square minus z minus 2. That implies f of a is 2a square minus a minus 2. So the answer is 2 pi I into f of a. 2 pi I into 2a square minus a minus 2. This is the value of g of a. This is the value of g of a. Now it is required to calculate g of 2. So put a equal to 2. G of 2 is 2 pi I into 2 into 4 minus 2 minus 2. 2 pi I into 8 minus 4. So 8 pi I. So if the point z equal to a lies inside the circle, then g of 2 is 8 pi I. If the point z equal to a lies inside the circle, simply outside the circle, simply we put 0. The integral is 0. So like this, we can evaluate the line integrals of the given functions along the given curves depending on the singular points, whether they lie inside the circle or outside the circle. If the singular point lies inside the circle, apply Cauchy's integral formula. If the singular point lies outside the circle, apply Cauchy's integral theorem. Coming to the third problem, let C denote the boundary of the square whose sides lie along the lines x plus. So here C x equal to plus or minus 2 and y equal to plus or minus 2. Evaluate the first question. Along C, e power minus z by z minus pi I by 2 dz. So here the singular point is z minus pi I by 2 equal to 0. So z equal to pi I by 2. So this is the singular point A, pi I by 2. Now the singular point pi I by 2. Now the value of this pi I by 2, 22 by 7 by 2 into I. So if you calculate this, you will get approximately equal to 1.6 something. And here this is plus or minus 2. So lies inside the circle. Inside the circle C. So therefore by Cauchy's integral formula, the line integral f of z by z minus a dz is 2 pi I into f of a. So 2 pi I. Now what is here? E power minus z is the function, z minus pi I by 2 in denominator. So f of pi I by 2. Now f of z is e power minus z. F of pi I by 2 is e power minus pi I by 2. So 2 pi I into e power minus pi I by 2. This is the value of the line integral for the first function. Similarly, the second question. Line integral cos z by z into z square plus 8, z into z square plus 8 dz. The singular points. How to find the singular points? By equating the denominator to 0. So we get the singular point z equal to 0 and z square equal to minus 8, z equal to plus or minus I root 8. So now plus or minus I root 8 are the singular points and also z equal to 0. And here x equal to plus or minus 2, y equal to plus or minus 2. So here z equal to 0 lies inside the circle C. which is x plus or minus 2 and y plus or minus 2. That's why z equal to 0 lies inside the circle. Whereas plus or minus I root by I root 8 lies outside the circle. So hence the line integral for this line integral is 0 using Cauchy's theorem. And now by Cauchy's integral formula, integral f of z by z minus a dz is 2 pi I into f of a. This is the statement of Cauchy's integral formula. And now f of z is cos z and f of a is cos 0 is 1. So this is equal to 2 pi I into f of a is, okay, just wait. Here we need to rewrite this function. So what is the given function? Cos z by z into z square plus 8 dz. This is equal to the line integral cos z by z square plus 8 whole divided by z minus 0 dz. So f of z is cos z by z square plus 8. Then what will be f of 0? Since 0 is the singular point, cos 0 is 1 by 8. So the answer is 2 pi I into f of 0 is 1 by 8. So pi I by 4. Similarly, there is the third problem, z by 2 into z plus 1. The third one, integral z by 2 into z plus 1 dz. So here first by equating the denominator to 0. So here 2z plus 1 dz. So the function is 2z plus 1 dz. So again from here 3 line integral c z by 2z plus 1 dz. So here take 2 common, z plus 1 by 2 dz. So this is line integral z by 2 by z plus half. Now the singular point is z plus 1 by 2 equal to 0, z equal to minus 1 by 2. So clearly z equal to minus 1 by 2 lies inside the circle C. Therefore, by Cauchy's integral formula, the line integral z by 2z plus 1 dz is 2 pi I into f of minus 1 by 2. And what is the function here? F of z is z by 2. So f of minus 1 by 2 is minus 1 by 2 by 2 minus 1 by 4. So the answer is 2 pi I into minus 1 by 4, which is minus pi I by 4. So in these three problems, we have evaluated the line integral using Cauchy's integral formula. So today I have introduced and discussed about the Cauchy's integral formula. In fact, we have two different things, Cauchy's integral theorem and Cauchy's integral formula. So depending on the singular point, what is singular point? The point at which the function fails to be analytic or ceases to be analytic, fails to have derivative, that is called singular point. If the singular point is outside the circle, then apply Cauchy's integral theorem. If the singular point is inside the circle, apply Cauchy's integral formula. So by applying Cauchy's integral theorem, the result or the line integral vanishes, is equal to 0. Whereas Cauchy's integral formula, the line integral in a particular format fz by z minus a dz is 2 pi I into f of a. So these are the things we have discussed in this today's session, and also we solved some problems on Cauchy's integral formula. I am going to continue the same in the next session. I will apply Cauchy's integral formula and both formula and theorem to evaluate the line integral of the given function in line integral C f of z dz. So, we evaluate the line integrals using Cauchy's integral theorem as well as formula in the next session. This is for today's session. Thank you very much.